Hello students, in this lecture we are going to continue the discussion on positive, definite and semi-definite matrices that we started in the previous lecture. Just a quick review, we defined positive definiteness, we made the connection to eigenvalues and we looked at a variety of properties. Okay? One among them was that if A is a positive definite matrix, so is P transpose AP for any P, okay, that has linearly independent columns. Right? Similarly, if A is positive semi-definite, then P transpose AP is positive semi-definite no matter what P is. Okay? So these were some of the properties that we discussed. Right? We said that if A is a positive semi-definite matrix, then any principal submatrix is also positive semi-definite. If A is a positive definite matrix, similarly every principal submatrix is also positive definite. Related to this, we also defined Sylvester's criterion, though we did not give a proof, which said that so long as the leading principal submatrices, that is the principal submatrices formed by taking increasingly larger matrices from the top left, have a positive determinant, then the overall matrix is positive definite. Okay. What we are going to do is continue. For example, just to cap off the review, suppose we have a 2 cross 2 matrix, right? So A11, A12, A21, A22. Okay, of course I'm going to assume symmetry here. So A12 will be equal to A21. Okay. Needless to say, we always deal with the real matrices in this course. Most of the things that we discuss can also be extended to complex matrices. We are going to make a brief note about that in the end of the course. Suppose you have a 2 cross 2 matrix like this, symmetric matrix. What is required? What conditions do these coefficients need to satisfy for this matrix to be positive definite? Right? So there are many ways you could see this, right? So one way to do this is to make sure that the eigenvalues are both positive, right? So how do you make sure the eigenvalues are positive? Well, it's a 2 cross 2 matrix, so it's quite simple. The eigenvalues will be roots of a quadratic. If you write down the characteristic polynomial, you get a degree 2 polynomial. The roots will be quadratic, right? So we can very easily write down the roots. The most important thing to see for the roots of a quadratic to be positive is to make sure that the sum of the roots is positive and the product of the roots is positive, right? So in this case, the sum of roots is simply the trace of the matrix, is it not? The sum of the eigenvalues is the trace of the matrix. So the trace of the matrix must be positive. So A11 plus A22 must be positive, and the product of the eigenvalues must be positive. Of course, the product of the eigenvalues here is the determinant of the matrix. So A11, A22 minus A12, A21, which is just A12 square. Okay, minus A12 square must be positive. These are the conditions that must be satisfied by the coefficients for a 2 cross 2 matrix to be positive definite. Well, let's parse these conditions a bit more. So this condition over here is actually saying A11, A22 is bigger than A12 square, right? So in other words, this product must actually be bigger than a non-negative number, right? A12 square can never be negative, right? So that actually means also as a corollary that A11, A22 must be same sign. Okay, because if they are opposite signs, then this product over here becomes negative and that can never be bigger than a square, correct? So A11, A12 must be of the same sign, and now you combine that with this, right, to conclude that both A11, A12 A22 must be positive. So you must have A11, A22 positive, and you must have A11, A22 bigger than A12 square. So these are the conditions that need to be satisfied for the 2 cross 2 matrix to be positive definite. So you can make a very quick check when you see a 2 cross 2 matrix, right? This we knew anyway, right? I mean, this is actually just saying that the diagonal entries must be positive, which we knew that anyway, right? For a positive definite matrix, the diagonal entries must be positive, right? So in fact, these conditions that you wrote down will be exactly the same. Let's say if you write down the Sylvester's criterion. So recall what the Sylvester's criterion is. It says that you start from the top left and apply that all the matrices have positive determinant. So here you will say A11 is bigger than 0. That will ensure that this matrix has a positive determinant. And then you will go to this matrix to ensure that this matrix has a positive determinant. That will give you A11, A22 minus A12 square is positive. Okay, so you'll get exactly the same conditions as here. Okay, so this is what it means for a 2 cross 2 matrix to be positive definite. Okay, So positive semi-definite, basically the same things with greater than 0 replaced with greater than or equal to 0. Right? That's about it. Okay. So today's topic is going to be quadratic functions. So this is what we are going to talk about today. And why are we taking the leap suddenly to quadratic functions? Hopefully things will become a bit clearer in this lecture. We already discussed quadratic forms, right? So if you recall, the definition we gave for quadratic forms at the very beginning was that it's an expression in n variables where each term is degree 2, right? Each term is degree 2. That's a quadratic form, right? A quadratic function is simply a function that also allows for degree 1 terms, right? So it's an expression in n variables. Each term, so it's a polynomial essentially in n variables. Each term has to be either degree 2 or degree 1 or constant. Okay, so you're also going to have degree 2 terms. For example, in one variable case, right, so just have one variable x, then the following is a quadratic function, ax square plus bx plus c. Okay, this is one of the first things you study even in high school, for example, right? You try to understand what are the roots of this equation, right? How do you solve ax square plus bx plus c equal to 0, right? What is the minimum value of this function? How do you find the minimum value of ax square plus bx plus c? Correct? All these things we have studied already. So this is for one variable case. Now we are going to generalize the same thing for many variables. Okay, let's go into the topic of this lecture. In particular, we are going to be very interested in minimizing. Okay, so let's actually look at minimizing the corresponding one variable. So what does minimizing here mean? Minimizing means in the one variable case, it means finding an x. Okay, so here x is a real number, right? So x is a real number, ax square plus bx plus c. You have to find the real number x such that this expression takes the smallest possible value among the whole real line, over the whole real line. Okay, what x do I pick such that the value of this is minimized? Okay, so do we know the answer for this for a single variable case? How do we actually solve this for a single variable case? There are many ways to do it, but we all know the form, right? I mean, we can actually plot this function. We can very easily plot the function, and we know how the plot of this looks like, right? So if this plot, so if you plot this on the x-axis here, and let's say this is my f of x, and I plot f of x here on the y or the vertical axis, right? Then we know that this is going to be a parabola, right? We have studied this earlier. This is going to be a parabola. Now the parabola could either be upward open or downward open, depending on a, right? Depending on what this a is, correct? So if a is positive, it's actually an upward open parabola. Okay, meaning that it's actually going to look something like this, correct? This is a positive case. If a is negative, it's going to be a downward open parabola. So something like this, and a is negative. Okay. So clearly, if you are trying to find a minimum value, then it doesn't really help to look at this case at all, because in this case, you can see that the function simply keeps on going down to minus infinity, right? So as you keep increasing the value of x, as you keep increasing x, the function keeps going downward and downward all the way up to minus infinity. Similarly, if you keep decreasing x also, the function keeps going down all the way to minus infinity, right? So when a is less than 0, there is no point in actually minimizing this, right? But when a is positive, then what you actually get is that it's a straightforward, the minimum is actually going to be at this point, and everybody knows where this point is actually going to be. It's actually going to be minus b by 2a. We'll see this. It's very easy, most of you know how to do this, right? There's minus b by 2a. That's x equal to minus b by 2a is the minimum. Okay. Of course, there's another scenario. What if a equal to 0, right? What if a equal to 0? If a equal to 0, then this just becomes bx plus c, right? So it's just going to be a line, right? So if a equal to 0, then it's going to be some line. Just draw it for illustration purposes. Is a equal to 0. Okay. In this case also, it doesn't make sense to talk about the minimum, does it? If a equal to 0. And in a equal to 0 also, it doesn't make sense to talk about the minimum, because if you keep decreasing x, then the function keeps going to minus infinity, right? Of course, what is the slope of this line, right? The slope of this line depends on what b is, right? So if a is 0, then it's bx plus c. The slope is basically b, right? So if this is the illustrative scenario when b is positive, right? If b is negative, then you'll get a line like this, right? But even then, you can see that as x keeps on increasing, the function keeps on going to minus infinity. So even here, it is unbounded. Okay, so this is what we call unbounded, right? Unbounded below. Call it unbounded below, meaning that it keeps going to minus infinity. It's possible to drive the function to minus infinity. That's what unbounded below is. Of course, if b equal to 0, then you get slope 0 line, which is just going to be completely horizontal, right? In this case, of course, every point is a minimum, right? Because the function plot is simply horizontal, right? If a is 0 and b is 0, then the function value is just c. So it's c. Every point is a minimum, right? So it's not the trivial case. Okay. So we only need to focus on the case when a is greater than 0 or a equal to b equal to 0. Right? These are the only cases we need to worry about if we have to talk about a minimum existing. Right? Otherwise, the minimum is minus infinity and we forget about it. Right? And out of these two, this is the only case where we have a unique minimum. Right? This is the only case we have a unique minimum. Okay? Because in this case, a equal to b equal to 0, basically the function value is c, so every point is a minimum, as I said, right? So if you want a unique minimum, you better have a positive, right? Okay, so now just going through the analogy that I mentioned in the last class, let us write down a higher dimensional quadratic function. So quadratic function in n variables. Okay, so the n variables are x1, x2, xn, and we write them as a vector x to b, x1, x2 to xn. Okay, then a quadratic function is actually something like this. This is the definition. Okay, so a quadratic function is x transpose ax is a quadratic form, but you also allow degree 1 term. So x transpose ax plus b transpose x plus c. Note the similarity to the one variable case, ax square plus bx plus c. Okay. In one variable case, you have ax square plus bx plus c. Here you have x transpose ax. So this term, the square term, is replaced with a quadratic form. The linear term bx is replaced with an inner product, and the constant c stays as it. C is not a vector, so I don't have to put an underline here. C is just scalar c. Okay. So this is a quadratic form. Okay. And drawing a direct analogy to the one-dimensional case, this is a theorem that we are going to consider proving in this lecture. Okay, a quadratic function x transpose ax plus b transpose x plus c has a unique minimum if and only if. Can anybody guess what happened in the 1D case? In the 1D case, we had a unique minimum if a was positive. Right? We have a unique minimum if and only if the matrix A is positive definite. Okay, the matrix A is positive definite. That's what we are going to prove in this lecture. Okay, so positive definiteness is innately connected once again to minimum values or existence of a minimum of quadratic functions. Okay, so in fact, if A is not positive definite, according to this theorem, if A is not positive definite, then this function will not have a unique minimum. So either it's going to have many minima, okay, or the minimum value is just going to be minus infinity. Okay, it's going to be unbounded below. Okay, if A is not positive definite. Okay, so that's the main idea. The intuition is very similar to the 1D case, right? So you cannot go wrong if you properly understand the 1D case. Okay, fantastic. So what we'll try to do now is we'll try to give a proof for this, right? This is once again an if and only if statement, and we need to prove it two ways. Okay, so we'll try to prove part 1. Okay, so a quadratic function, let's give this a name. Let's call this f of x, right? Just so that it's easy to notate to it. F of x has a unique minimum. Implies A is positive 7. Let's try to prove this part first. Okay, the next part we'll try to prove the reverse. Okay, fine. Okay, so now suppose f of x has a unique minimum. I want to prove that a is positive definite. Okay, so to prove that a is positive definite, all I need to do is make sure all its eigenvalues are positive. Correct? That's what I need to prove. Okay, so I need to rule out the possibility that there is some eigenvalue which is negative, and I need to rule out the possibility that there is some eigenvalue that is 0. Okay, fine. So let's try to look at the negative part first. Okay, suppose a has a negative eigenvalue. Okay, okay, so let's say that's lambda. Lambda is a negative eigenvalue, okay, meaning that lambda is less than 0, and v be the corresponding eigenvector. Okay, the corresponding eigenvector is v. Okay, so av is equal to lambda v, and lambda is negative. Okay, so here is what I'm going to do, right? I'm going to, in this quadratic function over here, x transpose ax plus b transpose x plus c, I'm going to set x to be a multiple of b. Okay, so I'm going to set x to be alpha b. Okay, and vary alpha. So alpha here is a real number. Okay, set x to be alpha v and vary alpha. What does this mean geometrically? What I am doing here is I have some eigenvector of the matrix. Let's say this is my eigenvector v, so unit vector. What I'm trying to do is I'm trying to look at x that's a multiple of v, meaning I'm actually trying to move on this line. Okay, I'm trying to move along the line pointed by the eigenvector, okay, corresponding to the negative eigenvalue. Is that okay? So I'll try to look at what happens to this function f of x along this line. This is a very popular, very common trick that we use to understand high dimensional functions. High dimensional functions meaning functions of many variables, right? Because we cannot even plot a function of many variables, correct? To plot a function of 2 variables, you need to use 3D, right? To plot a function of 3 variables, you need 4D, and we really cannot imagine how that is. So to get an intuition, what we do is we restrict our function to one line. Okay, and we see how the function behaves on that line. Okay, that we can understand, because once you restrict a function to a line, it becomes a single variable function. Alpha is my only variable now because I have restricted it to this line. Okay, alpha completely dictates the value of the function. Okay, so fine. So let's set x equal to alpha v in the quadratic function over here, and then what we will get? We will get alpha square times v transpose av plus alpha v transpose b plus c. Correct me if I am wrong here. I think it is b transpose b, but it's the same as v transpose b. Okay, so this is what you will get, right, if you move along that line. Okay, so now v transpose av is just lambda, so you will get something like alpha square lambda plus alpha v transpose b plus c. Okay, as I told you, effectively alpha is the variable here, right? As you keep varying alpha, you get all these points, correct? So if you were to consider the plot of this function with alpha on one axis and the value of the function f of x, f of alpha v, that is on the f of alpha v on the vertical axis, then what you will get essentially is going to be a plot of this function, and we already know what that is. You're going to get a parabola, right? Okay, but what's the catch here, right? Is going to be an upward open parabola or a downward open parabola? Of course, that depends on what lambda is, right? And I started with the assumption here that lambda is negative. I started with the assumption that lambda is negative. So this is going to be a downward open parabola, of course, something like this. Okay, and that means that I can simply keep increasing the value of alpha, and I'll get ultimately very, very negative values of the function f, right? So this is f of alpha v. Okay, so the function value will become increasingly negative by taking a very high value of alpha or a very low value of alpha for that matter, right? Alpha very positive, close to infinity, or alpha very negative, close to minus infinity, will make this function close to minus infinity. Okay, so in some sense the alpha square term, this one dominates, right? So if alpha is very large, this term will dominate, and this term is always negative because lambda is negative, right? Okay, so that's the main idea. So this function is unbounded below. I can drive it as close to minus infinity as I want simply by traversing on the line corresponding to the eigenvector of the negative eigenvalue. Okay, but that's not what's given to us. We are given that the function has a unique minimum, right? That means that we cannot have a negative eigenvalue. No eigenvalue can be negative. Okay, that's done. So what else do we need to do? We need to roll out the possibility that we have a zero eigenvalue. Okay, fine. So let's assume, suppose A has a zero eigenvalue. Okay, and let's say V be the corresponding eigenvector. Okay, V be the eigenvector corresponding to zero eigenvalue. Okay, suppose we have that. Okay, now zero eigenvalue typically means AV equal to 0, right? So what happens when you do alpha V, right? You do the same computation as before. You are simply going to get alpha V transpose B plus C. That's what we'll get, right? F of AV equal to alpha V transpose B plus C. So once again, as you vary alpha, what do you get? You get a line, okay, of slope V transpose B. Okay, so if the slope is non-zero, V transpose B is non-zero, then if the slope is non-zero, then it's either a line that's increasing or a line that's decreasing. In either case, it's unbounded below. Okay, if the line is increasing, then simply by making alpha more and more negative, I'll get a value that's close to minus infinity, right? If the line is decreasing, then by taking alpha very large, I get a value of the function that's close to minus infinity. In either case, it's unbounded below. Okay, so the only possibility for us to consider is when V transpose B, the slope is exactly equal to 0. And if the slope is equal to 0, then this line just becomes a horizontal line. Okay, the slope becomes 0, this line becomes a horizontal line. In other words, the function value is C at all points on this line. Okay, so f of alpha V equal to C. Okay, else, so if V transpose B equal to 0, then f of alpha V is equal to C, right? And the minimum is not unique. Okay, it's not unique because picking any alpha will give you the value C, the minimum value C. Okay, the minimum is not unique. So you cannot even have lambda is equal to 0. Okay, so the only possibility left for us is that lambda is positive. Okay, okay, so basically this applies to any arbitrary eigenvalue. So this proves part 1. Okay, this proves that if your function has a unique minimum, then A is the matrix A has all positive eigenvalues, or in other words, it's positive definite. Okay, fantastic. So now let us look at the reverse or the converse direction. Okay, the converse direction is if A is positive definite, then f of x has a unique minimum. F of x has a unique minimum. Okay, so how do we go about doing this, right? So here what I'm going to do is, the proof I'm going to give is going to be constructive, in the sense that I'm actually going to give you the minimum value and the corresponding x that minimizes. Okay. So let's go back to the single variable case. We have ax square plus bx plus c. Okay, in the beginning of this lecture we said the minimum occurs at x star equal to minus b by 2a. How do we get that? How do we get x star equal to minus b by 2a? There are many ways to do it. Of course, I think most of us right now have this muscle memory to just take the derivative, set the derivative to 0, and that's what will give us minus b by 2a. Okay? But let's avoid calculus for now, because multivariable calculus is a bit complicated. It's not possible to do multivariable calculus without doing positive definiteness, right? So we'll run in circles, right? So you don't want to do that. So what I'm going to do is, we will use another very powerful technique, which again most of you already know, called completing the square. You'll run into this technique quite a lot, especially when you do probability, right? Completing the square. What does completing the square mean? The main issue we are having here is with this term, is it not? Is with the linear term, right? So if we didn't have the linear term, right? So let's say we had ax square plus c, right? if we did not have the linear term, it's very clear what the minimum must be, right? What is the minimum? Because see, this is a constant term that doesn't depend on what x you pick. This term is the only term that depends on x, and the smallest this term can be is 0. We simply set x equal to 0, right? So that's the minimum. So here for this function, we simply have the minimum is 0 and the minimum value is c. Very straightforward and very simple, correct? So the problem is being caused by this term. So the idea is to get rid of that term somehow, to get rid of that term by somehow including that in the square term. So you only need to have square terms and not a linear term, right? To do that here, what you will do is simply, let's just take a common here, right? We will simply write it as x plus b by 2a whole square. Okay. Again, many of you might have seen this trick. It's widely used. This goes right for the sake of those who haven't seen it, right? So a times x plus b by 2a whole square. Okay. So now what this will do is, when you expand this, you will of course get x square, right? But you will also get so you'll also get, remember, b square by 4a square. You'll get that. But you'll also get this term, right? xb by a. That term you'll also get, right? So when you multiply it with a outside, you'll get ax square plus bx, right? Plus something else. But you have already covered both the degree 2 term and the degree 1 term, right? Whatever is left is a constant, right? In fact, what you left here, let's write it down. It's just going to be b square by 4a. Okay, that's what you're going to get, right? Now, to make this thing equal to c, what we'll do is we'll plus c minus b square by 4a. That's what we'll do, right? So you'll see that this expression over here is actually equal to this expression. Okay. Now what is the advantage of this expression is, here you have essentially all the variable is contained within a square, right? It doesn't spill over into a linear term. It's just like here, correct? So this expression is very easy to minimize. The minimum value of this will happen when this whole thing is 0. Okay, in other words, when x is equal to minus b by 2a. Okay. Incidentally, this is actually what gives you that formula, right? It's minus b plus or minus square root of b square minus 4ac by 2a or something like that, right? That formula, the supposed formula for finding the roots of a quadratic, comes directly from this, just by completing the square. Okay, so we will do exactly the same thing for these vector, multidimensional quadratic functions, right? So let's rewrite f of x. F of x is x transpose ax plus b transpose x plus c. Okay, so what we did here is we replaced x with x plus b by 2a, right? Now in the higher dimensional case, of course, b has become a vector, right? In the multivariable case, b has become a vector. This a is actually a matrix, right? So I'm just going to write this whole thing as half of b inverse a. Is that okay? So I'm going to consider the following. Let's see what happens when we write x plus a inverse b by 2 transpose a x plus a inverse b by 2. Okay, let's just write down this term and see what happens. We'll see whether we have covered both the square term and the linear term here or not. Okay, so let's just expand this thing out, right? So I'll leave it to you as an exercise, but I'll just go through it very, very fast anyway. It'll be easy. So this term over here, x transpose ax, will give you x transpose ax, right? If you just look at these three terms that I'm circling here, that will give you x transpose ax. Just do some coloring. Okay. X transpose ax, that just gives you x transpose ax. Okay, fine, fantastic. Now let's actually look at some other terms. So what about these three terms, right? These two terms, this one. Okay, that's going to give me, so if you take the transpose, right? So if you take the transpose of this expression here, you get b transpose a inverse transpose. Okay, a inverse transpose is just a inverse, because a is symmetric here, a inverse is also going to be symmetric, right? So just asymmetric, a inverse also symmetric. Okay. Is this clear to everybody, by the way? If a is symmetric, why is a inverse symmetric? So in fact, you can actually write an expression for A inverse. No, A inverse is V D inverse V transpose. Correct? That's why A inverse is also symmetric, right? You can use that to say if you want. Okay. So then what are you going to get? You're going to get. So let's see what you will get. You will get B transpose. Correct. There's going to be a factor of 1 by 4 that will come. You will have A inverse A inverse B. Okay, this is the expression you will get, right? Now A inverse A, there are multiple A inverses here, so these two I can just remove and write B transpose A inverse B. So that's what I'm going to write. Okay, so this is the next term that will come up here. Okay, and then you will have the cross terms, right? The cross terms that are obtained by taking x here, okay, x here, and A inverse B by 2 here, right? So that's going to be, so let's just write it down, x transpose A and A inverse B by 2. Okay, so that just gives you B transpose x by 2, right? And similarly, when you take the other cross term, you are going to get the other half. Okay, when you do everything, you will actually get plus B transpose x. Okay, so as you can see here, you've already covered both the quadratic and the linear term, and you are just left with C over here. Okay, so to get C, what I have to do is I have to subtract this term and I have to add C to this expression. Okay, so that's why I'm going to write like this: f of x equal to x plus A inverse B by 2 whole transpose A x plus A inverse B by 2, okay, plus C minus 1 by 4 B transpose A inverse B. Okay, that's what I'm going to write. Now from this it's clear exactly. Okay, so if I want to minimize this function, what do I do? So first of all, remember that this part over here is constant. It's unaffected by this part over here is a constant and unaffected by x. This is the only part that depends on x. Okay, but then if you look at this whole thing as basically a y, you have y transpose a y here, right? And a is given to be positive definite, right? So in this part, we're actually starting with the assumption that a is positive definite. Okay, if a is positive definite, then the smallest value of y transpose ay has to be when y is 0. Okay, because y transpose ay is always positive otherwise, right? So the only minimum for this will happen at y equal to 0. That's the unique minimum. Okay, for a quadratic form, correct? So that means it has a unique minimum at x equal to minus A inverse B by 2. Okay, so okay, x equal to minus A inverse B by 2. Okay, that's actually the minimum. I'm actually giving you construction. Okay, this mirrors the B by 2A that you get in the single variable case. It's exactly the same. Just A inverse B by 2 it became, right? Higher dimension. And the minimum value is C minus 1 over 4 B transpose A inverse B. Okay, so when you make x to be equal to this, then this whole term becomes 0 and this is the minimum value. Okay, and this is the minimum value. Okay, so I think this is a good thing to remember also. It's very useful. Okay, this is the unique minimum of a quadratic function if a is positive. Okay, so this proves the equivalence, right? This proves the theorem that we started out with in this lecture. Has a unique minimum if and only if a bigger than 0. In fact, to this we can add the unique minimum is given by minus A inverse B by 2 and the minimum value is C minus 1 by 4 B transpose A inverse B. Okay.